Yes, questions. I know that today at least we have some questions. Okay, what was the question? Okay, I don't remember the question, so you should repeat the question. Okay, so this was the question. Now I remember it. We had this example. We have two identical capacitors connected in series, and they are both connected in parallel to a third capacitor. This whole thing was connected to a battery. Now the question was, so how are the charges in this capacitors, let's say one A, B, and C? So how are QA, QB, and QC related to each other? Now, one thing we know is Q is V over V times C. Okay, this is how the charge of a capacitor and the potential of a capacitor are related. Now, let's say the potential, remember, this V is the potential difference across the ends of the capacitor, not of the system. This Q is the charge in the capacitor. This V is the potential difference between the two plates in the capacitor. So let's look at this configuration first. The potential difference across the capacitor C is how much? No, we don't know QC, so we know this V, the potential of the battery. It's just V. Now, what about VA? Which will be equal to VB? It's V over 2. Now, remember, these two capacitors are identical, and we know that the V is nothing but the sum of the potential differences across the A capacitor and the B capacitor. Now, since they are identical, it's kind of, you would expect that the potential differences across both of these capacitors to be the same. Since their sum is V, so this should be V over 2. So you see, since they are all identical capacitors, we know that Q is proportional to V in all of them. Q is the charge of each one of them is proportional to the potential difference across the capacitors. So you can just say that QA, which should be equal to QB, which is less than QC. This is what happens before, when the battery is connected, so that because the battery makes sure that these 2 points have the same charge. Okay, so what happens when you remove the battery? Why should they? So your friend is saying this one. So let's say we have these two capacitors. Now, if we would start from such a configuration, now you can say that everything is connected in series to each other, and now you see the problem with thinking of this as everything is connected in series. Now let's remember how the charges look like in capacitors connected actually in series. So you have these 3 capacitors. This is positively charged, this is negatively charged. Positive, negative, positive, negative. So in series connection, the charges in each one of the capacitors, they are alternating. So the negative plate is connected to the positive plate of the other capacitor. Now let's look at this configuration. And this one, how are the charges? Now this is the positive terminal, this is the negative terminal. So we know that these plates are positively charged, both of them. This is negatively charged. This is positively charged, that is negatively charged. Now, if you look at here, okay, in these two terminals, they are connected in series, we know, and the charges in the place are alternating. The negative terminal of negative side of one capacitor is connected to the positive side of the other one. But if you look at this one and this one, the negative plate of this one is connected to the negative plate of the other one. So even if you remove this battery V, as in this configuration, still we have these are positive, negative, positive, negative. This is positive, this is negative. This is not a series connection. In a series connection, we have the negative terminal should be connected to the positive plate. The negative plate should be connected to the positive plate. So in a sense, nothing changes. Because you can also think of it like this. The capacitor just behaves like a battery. It already keeps the original potential difference between these 2 points. Sure, there is a potential difference. I mean, you see, here it was the battery that created the potential difference. And once you remove the battery, the capacitors themselves, they keep the potential difference the same. Now, you see, if you look at this one, okay, what can happen? It is possible, one might think that maybe the positive charges from here will flow to this positive plate over here, and the negative charges from this plate will flow to the negative charges over there. Right? That's one thing that one can think about, one possibility, maybe. But you see, if positive charges are moving in this plate, and the negative charges of this plate moves to this plate, what you are actually doing is you are increasing the charges in these capacitors. But if you are increasing the charges in these capacitors, then you are also increasing the potential difference across each one of these capacitors. So if the charges would flow from this capacitor to these two, you are increasing the potential difference between these 2 points. Let me just write x, y, and z. This is point x, y, z, and t. Now, if charges would flow from this capacitor to this one, you are increasing the potential difference between the points x, y, because these capacitors now have more charge. And you are reducing the potential across this capacitor, because since the charges are going away to the other capacitors, the potential difference across this z and t, you are reducing the potential difference between the points z and t. But the problem is, since this is a conductor, the potential difference between z and t and the potential difference between x and y, they have to be the same. Because x and z, they are on the same conductor. Y and t, they are on the same conductor. It has to be the same. So charges cannot flow from this capacitor to the other 2 capacitors. Well, in the other way around, you can say, okay, maybe the positive charges from this plate are from these capacitors are flowing to this capacitor. But then the same problem. If the charges flow to this capacitor from these 2 capacitors, then you are lowering the potential difference between x and y, and at the same time increasing the potential difference between z and t. But that is also not possible. The potential difference between x and y and z and t, it has to be the same. So charges cannot flow when you remove the capacitor, when you remove the battery. Well, what we are actually doing is just studying some of the circuit elements we have. I mean, this is one possible circuit element. Whichever circuit element you have, whether it's the capacitor or the resistor that we will start studying this week, or we will even have an inductor in a couple of weeks, we will study inductors, or we can even think of other sophisticated surface elements like the diodes and the transistors. You can connect everything in series, or everything in parallel, or just a mixture of 2. This series connection and parallel connection is valid for any circuit element. And the main difference is, in a series connection, well, we will be studying currents now. The same current runs through all your circuit elements, whether they are resistors or capacitors. That is what is actually the series connection. In a parallel connection, different currents are running through each one. And again, for resistors, we can define some series and parallel connection. For capacitors, we can define, so we can even think of some mixed circuits where a resistor is connected to a capacitor in parallel or in series. Plate. Okay, so, well, you can say that the battery here is connected in series to the system. Well, another question, okay. Your friend is asking, what happens if they are not identical capacitors? So let's just take the same example. Connect them to a battery. This has capacitance CA, CB, and CC. And this is V. We still know that Q is equal to C times V. Nothing would actually change even if they were not identical capacitors. Because what we know is, okay, the potential difference across the capacitor C is definitely V. And the potential difference across capacitor A plus the capacitor B is also V. Or VA and VB, they are definitely less than V separately. Now, this tells me that I cannot really say anything about QA and QB, whether they are equal or not. The only thing I know is that they will be smaller than the QC. Oh, sorry. There's one catch over there. You see, if C's are all different, well, I can order somehow the potentials, but I cannot say anything about capacitance times the potentials. I don't really know. We have to do some more work to determine whether how they will be. Now, what we can say, CA times VA plus is equal to CB times VB, because the charges in each one of these should be the same. This is what we can say. And whether CA or CB, which one is larger, it will determine. Yeah, this already tells me that QA should be equal to QB. This will always be true because they are connected in series. I cannot really say about CC. Depending on its capacitance, it can be larger, it can be smaller. No. There is nothing that creates a potential difference between X and Z. No, I'm just saying X and Y, the difference between X and Y. And the difference between Z and T, they should be the same. The difference between the potentials of the point X and Z, it should be 0. I'm not really saying anything about the potential of this point X. It's not actually defined without choosing a reference point. But the potential differences are always well defined. Other questions? Now let me just correct some notations. Okay. So here. Now this kappa is not the dielectric constant that is defined in your book. In your book, the electric field is defined as E0 over K. This is the dielectric constant. It doesn't really make any difference in the concepts, but if you want to use some tables somewhere, for example, in your homework, you will have to use the tables. In that case, this is the dielectric constant that appears in your question, also in your book. Now, in terms of this dielectric constant, now this is still true. This, hold on, what's the mistake here? Okay, this is still true. It's increasing the capacitance. This is just a mistake over here. Now let's study the forces acting on a dielectric. Now let's just assume we have this capacitor, and we just place a dielectric in between. This is my dielectric with dielectric constant K. It's not fully immersed. I mean, let's say that this part has area A1, and this part has area A2. And A1 plus A2 is equal to A. Now, the first question we will ask, what is the energy stored in this capacitor? And let's say that we create a potential difference, or what's the capacitance? Let's start with the capacitance. What is the capacitance of this system? And once we determine the capacitance of the system, the next question I will ask is, what is the energy stored in this system? Now, to determine the capacitance, you can either assume that there are different charge densities in this region and in this region, and calculate the electric field in both of these regions, equate the potential difference. That would give you an idea about what are the charge distributions in these two ranges. Or you can just separate this into two different capacitors. That will be the easier one. This is the same thing as one capacitor filled with dielectric that has an area A1, and another capacitor that is empty that has an area A2, and they are both connected in parallel. It doesn't affect anything in terms of the capacitance. Well, it will cause a slight change in the capacitance, which we are ignoring, because the charges on this plate will be uniformly distributed, more or less, on this plate and on this plate. It will create a more or less uniform electric field inside the dielectric, and that is what's important for us, because that electric field is what creates the potential difference. And we already know the capacitance of both of these regions, C1. Well, let's say C0 to be epsilon 0 A over D. This is my C0. C0 is the capacitance of the whole capacitor in the absence of the dielectric. Now, C1 will be, well, first of all, the total capacitance is proportional to the area. Now, the area is reduced to A1 over A. This is the area. Times C0. Well, this is the capacitance of this part of the capacitor in the absence of the dielectric. So when we put the dielectric, it increases the capacitance by the dielectric constant K. C2 is A2 over A times C0, because area is C2, A2, the capacitance is proportional to A. The fraction of the area is A2 over A, so the capacitance is reduced by that factor, and there's no dielectric. Now the total capacitance of this system No, you see, it is this K that changes the two. So these are the capacitances we have. Now they are connected in parallel. So the capacitance of my system, well, 1 over the capacitance of the total system is 1 over C1 plus 1 over C2, which is A over KA1 C0 . Yep. This is series. So C is equal to C1 plus C2. Which is K times A1 plus A2 over A times C0. This will be the capacitance of my system. Now let's simplify the problem a bit. Let's assume that we have these parallel plates. This is the second one. The dielectric is filling this region. Up to the other end. Now I'm just assuming the plates are kind of rectangular. And it fills all of one side, but only fills partially the other part. Let's say this part is L. Let's call this part, this length X, this whole part L. And so this will just give me K times X plus L minus X over L times C0. Because now the area is just this length multiplied by this length. Both A1, A2, and A, they both contain this factor of the length. So this is my capacitance of the whole system. Now when we were deriving the expression for the energy stored in a capacitor, remember the energy stored in a capacitor was 1 over 2 CV squared, or we didn't make any assumption about the capacitor. The only thing we used was that the charge was equal to C times V. That was the only thing we used. And we arrived at this energy stored in the capacitor. Now this is my C. I just need to put this C over here. Well, I can use this expression, or I can use this other one. They're both equal. So now we have this expression for the energy stored in my capacitor. You can take this one or this one, where C is given by that factor over here. So you see that the energy stored in the capacitor depends on X, how much you insert this dielectric. So let's suppose that you have this dielectric, you have this capacitor parallel plates, you have this dielectric, and as you change X, the energy stored in the capacitor changes. So where does that difference come from? We know that energy is conserved, but we have just seen that if we change this X, the energy stored in the capacitor is changing. So that energy should come from somewhere. So where does it come from if energy is conserved? Well, how does the I mean, you see, this energy is the energy stored in the electrostatic electric field. How does friction relate to electric field? If that is your claim. Well, you see, in none of these descriptions we had assumed anything about the electrons. I mean, the only thing we know is that there's something called the charge. What is it? We might not even know it. There's this quantity called charge. We devised this object called the capacitor from conductors. What are conductors? Probably we don't even know. We don't even use any property of the conductor except that the charge is free to move. And now we arrived at the non-conservation of energy, or did we? So where does that energy come from? Or where does the energy go to? Now suppose I just create these charges connected to the battery. So I create this potential difference. Then I remove the battery. The potential difference will still be there. The charges will still be there. Okay, I charged it. I remove the battery afterwards. It is charged. Now I am moving this dielectric, and the energy stored in this capacitor, which already has this potential difference, the energy stored in this capacitor is changing. So, I mean, what do you mean? It's the internal energy of the dielectric which is being transferred into the electric field. Well, let's say that there's no internal energy. We have to do work. The dielectric doesn't just move in or move out. This is our capacitor. This is the dielectric. We have to exert some force on this dielectric if we want to move it in or move it out. Or even if we just want to keep it over there, we have to exert some force. Now we can calculate the force because we know if we change x by, if this is the potential, U is equal to 1 over 2, let's say Q times V. This is another expression for the potential. So if we change the potential, we can determine how much the potential energy of the system is changing if we just shift it by dx. If we shift the dielectric by dx, we know how the potential energy changes. Now, if we want to conserve energy, this energy change in the energy should better be equal to F times dx, F times dl. Well, if dx and dl are in the same direction, this is F dx. So the force that we should exert to displace the dielectric by dx should be equal to du by dx. So this is the force that we should exert if we want to move it by dx. Oh, but that means even if we want to keep it over there, that is, if we send dx to equal to 0, we should still be exerting this force F, because the capacitor will be pulling this dielectric inside. So if we want to keep it out of this capacitor, we should still keep exerting this force F. Now, how do we take this derivative? So we have these three identical expressions for the potential energy. This one, this one, this one. So how should we take this derivative? Which one should we differentiate? 1, 2, 3. This one. Why? Yes, that's Q squared over C. Which one should we differentiate with respect to X? Well, a good question. If you want to take the derivative, you first have to identify what depends on your variables. Now you can imagine this isolated capacitor. If the capacitor is isolated, it means the charge cannot flow. So Q is constant. As you change this X, nothing changes. Nothing changes, no. The charge doesn't change. So in such a case, the charge will be constant. So it would be better to work with, let's say, this one, because this is only the C over here that depends on the charge X. Or you can even use this one. But V will be changing because C is changing with X. Or you can imagine the case when there is the battery that's connected to your capacitor. Now, if the battery is connected to your capacitor, in that case, the charge, we will just start studying it. The charges in the capacitor it can increase or decrease depending on how C changes, so as to make sure that the potential difference across the capacitor should be the same. Because the battery would keep the same potential difference, a fixed potential difference. But then we have other issues. How much of the work that we do has been done to the capacitor? How much of it has been done to the battery? So that we will have to pay attention to. Once we study the batteries, we will look at the same problem from the other perspective. Now let's just assume, not assume, for this time being, we don't yet know how much work the battery does, so we don't want to deal with it. So let's look at the case when we are not connecting my system to the battery, so that Q is constant. Well, if Q is constant, I can either take the derivative of this one. But Q is constant, that means C is changing and V is changing with X. So I have to differentiate V and C with respect to X. Well, why does V depend on X? Well, because Q is constant and C depends on X. So I would rather go with this one. Q, I already know, is constant. C is the only thing that depends on X. Now, just one more thing over here. Most of the time, you just take the X to be positive. Now, if you remember our definition of X, this is our definition of X. So if you think of the X as positive, you are not causing a displacement in this sense, but you are causing a displacement in the other sense. Yes. This is my dx. Or this one. Now the difference will be, I have a sign change over here. Just a little thing that you have to pay attention to. Now this time F would be the magnitude. F is the force in this direction. Now let's see, U is this one. Du by dx is equal to d by dx of 1 over 2 q squared over c. We know that c is the only thing that depends on x. This will be minus 1 over 2 q squared over c squared dc by dx. And we know what the capacitance is. It's over here. So we can just work the algebra. And you will see that du by dx would be equal to minus 1 over 2 q squared over c squared times k minus L over L times C0. Okay, now we have the expression. Let's try to interpret. Does it make sense? Does this expression make sense? Now, what do you notice about this force? What can you say about this force? Where does this force come from? Let's start with that one. We know that there has to be some force, we know that this force has to be there if we want to conserve the energy. We have to be exerting such a force on our dielectric, but where does it come from? Okay, good. Where's my electric field? So let's see, this is our capacitor. Now we have a dielectric inside. So where's the electric field? And what is the direction of the electric field? In parallel plates. We always say that they are homogeneous, they are vertical. So if this is positively charged, this is negatively charged. And so we also said that, okay, the electric field is in this direction. Inside the dielectric, it will be smaller than outside the dielectric, but mainly they are vertical. So how does this electric field exert a force on our dielectric? Okay, we already said that the dielectric is polarized, so the upper part of the dielectric is partially negatively charged. The lower part is partially positively charged. So what will be the direction of the force that the upper part of the dielectric will feel? It will be feeling a force vertically upward. What about the force that the lower part of the dielectric will feel? A downward. But we said that the force that we should be exerting is horizontal. Well, the vertical upward force and the downward force will, in fact, they will cancel each other. So how do we get this horizontal force acting on the dielectric? Okay, that creates the electric field. So how will I go from that potential difference to the fact that there is a horizontal force acting on my dielectric? Okay, we derived it, we know that it has to be there, etc., etc., but how does it come about? Your friend is saying friction force. So if I lubricate it, the force should change, or we don't have any friction coefficient in our dielectric. And remember, if we put the dielectric in between the plates, the direction of the force will just pull this dielectric inside the capacitor. So if you just let it over there, if there's no friction force, the dielectric will just move inside the capacitor. If there's friction force, of course it might stay outside, but ignore the friction force. The dielectric will feel a force that will, due to this electric field, which pulls it inside the capacitor. So how does that force come about? Fringing. You see, here the problem with these vertical straight electric field is that they can never create a horizontal force acting on my dielectric. But remember, we have these fringing fields, which means the electric fields are not really vertical. So if you go here, the electric field close to the edges, they will bulge out. So this is how they will look like. Of course, they will be perpendicular to the surface. So you see, at this point, there is an electric field in this direction. At this point, there is an electric field, no. At this point, the electric field is in this direction. At this point, the electric field is somewhere in this direction. Both the upper and the lower parts, remember, here we have negative charges, so they will feel a force in the opposite direction to the electric field. So both this region over here will feel an electric force in this direction, and this one will feel an electric force in this direction. Their vertical components will again cancel, but nevertheless we will have a net horizontal force which will be pushing this dielectric inside our capacitor. So again, this is another example where, although in most of our derivations we are ignoring the fringing effects, the fringing effects do come out to be important in certain phenomena, like the forces acting on our dielectric. The fringing effects should be there to create this force. Well, what do you mean by storing the electric field? Okay. I mean, we do use the terminology sometimes that the electric field lines can be trapped in certain materials, or the magnetic field lines can be trapped in materials. Such terminology we do use. But I mean, even in those cases, what is actually happening is that you are creating some charge distribution in your material, which makes sure that the now, I mean, this fringing effect, by the way, is independent of whether you have these dielectric or not. Even if you don't have the dielectric, there will be some fringing effects. Yeah, I mean, in some sense, yes, but I would rather if you wouldn't go to that terminology yet. Yes. Okay. Some kind of an oscillatory motion. I mean, if there is no friction forces acting on it, it will. For example, one way that you might be able to test this is take two parallel plates, take some pure water, put those plates in pure water and connect them to a battery. If this description is correct, the parallel plates should suck in the water. So the level of the water inside between your plates should increase. But you have to take pure water because pure water is not such a good conductor. If you don't take pure water, it will be a conductor, so you will be making a short in your circuit. Where? The horizontal forces in this one. Can you repeat your question? No. That's the electric field, remember. I have drawn the electric field. This is the direction of the electric field. The directions are correct. But you see, here we have negative charges. So the forces that these negative charges will feel will be in the opposite direction. Now here I just draw the electric field. This is the electric field line. So the tangent to that along these directions tells me the direction of the electric field. Of course, the force that this will feel, if you want, I can draw the forces also on this graph. So here I have some, here I have this force, and here at this point I have this other force. The force and the electric field are on the opposite direction at this point, because at that point I have negative charges. The force and the electric field are in the same direction at this point because I have positive charges over there. Other questions? Well, it depends on how you place the dielectric, but if you just place the dielectric symmetrically so that there are no gaps below, no gaps above, it's homogeneous, in that case it will be equal. Other questions? So see you after the break.